Welcome back to this next video in which we are discussing finitely generated field extensions. Okay, so in the previous video what we saw is that a finitely generated field extension can be built by a series of simple extensions. Okay, so for instance, if you want to build the field extension that's going to be generated by this finite collection of elements, alpha 1, alpha 2, all the way up to alpha n over f, then what you can firstly do is build the field extension of f, which is generated by alpha 1, then take that field extension and then from that extend that and build the extension of that that is generated by alpha 2, and continue on this process until you have insisted that all the elements alpha 1, alpha 2, all the way up to alpha n are in there. Okay, what I want to turn my attention to in this video is why should we care? Why is this useful? And now's the part where I'm going to say, okay, let these elements alpha 1, alpha 2, all the way up to alpha n be algebraic over the initial field f. This is going to give us an incredibly beautiful understanding of how to actually construct the field extension generated by alpha 1, alpha 2, all the way up to alpha n over f. Okay, so let's go on to the other side. Now, just like we did previously when we were describing the fact that any finitely generated field extension can be split into this series of simple extensions, I'm firstly going to illustrate this great theorem, if you like, okay, and I might as well put theorem 2 or something. I'll just put theorem here. So here comes the second great theorem of this video. The way I'm going to show you it, rather than trying to write down what it is, okay, I'm going to just show you it, and I'm going to show you again with the simple example where we're just trying to generate a field extension of f using two generators. Okay, and then we'll once again generalize it to an arbitrary finite collection of generators. Okay, so initially let's try and understand this theorem in the context of the field extension generated by alpha 1 and alpha 2 over f. Okay, so what's the big change now? The big change is that we're going to assume these elements are now algebraic over f. Okay, rather than before where we were just assuming that they were any old elements which could have been transcendental. So we're now going to assume alpha 1 and alpha 2, and I don't know why I've put r, it should be it should be r, okay, so r algebraic over f. So we're going to assume that they are algebraic over f. Now remember what algebraic over f means. Algebraic over f means that there is a non-zero polynomial in the ring of polynomials over the field capital F, such that these elements are the root of that polynomial. Okay, now, as we proved in the video on algebraic field extensions, if you have an algebraic element, there is always a minimal polynomial for that algebraic element, okay, which is the unique monic irreducible polynomial in the ring of polynomials over the field capital F, such that that element is a root of that polynomial. Okay, so let's say for alpha 1 we have its minimal polynomial, which I'll just write down here, the minimal polynomial, and then we subscript it alpha 1 to remind us that it's the minimal polynomial for alpha 1. We put a comma, and then also in the subscript there'll be f, because it's the minimal polynomial over f, and then of course it's in x. And similarly for alpha 2 we'll have the minimal polynomial for alpha 2 over f. Okay, and both of these polynomials are elements of the ring of polynomials over the field capital F, and they are the unique monic irreducible polynomials which these two elements respectively are roots for. Okay, so they are important, just to be aware of those. They'll be important in a moment. Okay, so now the question becomes, how can we understand the field generated by alpha 1 and alpha 2 over f by understanding that it can be split down into two simple extensions? So what we've just shown, what we spent the previous video showing, is that we can think of this as firstly extend f so that it now contains alpha 1, so build the extension of f generated by alpha 1 here, and then make a further extension to that, build the extension of f of alpha 1, which is generated by alpha 2 here. That's what we showed in the previous video. Okay, now, it will help just to copy the picture of this out again for an understanding point of view. So I will just spend a little bit of time now redrawing out the picture that we had on the previous page. So here is our larger field, capital L, which we're working in. Here is our smaller field, capital F. Okay, and let's add a bit of colour onto here. So let's have L denoted in red here, and we'll have F denoted in green. Okay, so now let's draw on the right hand side here, or the underneath of this equation here, this bit here. Okay, so we've now proven that this is equal to this, so if we want to build this we can just consider building this. Okay, so if we want to build this, we firstly generate the field extension of F, which is generated by alpha 1. That will be this portion, F of alpha 1 here. Okay, and I'll highlight that up in orange, or highlight the outsides of that in orange. Okay, so that's the smallest field that contains F and alpha 1, and then now to build the final thing you want to now build an extension of this, generate the extension of this that now contains alpha 2. Okay, so let's colour that final thing in vivid purple here, and this is the final field extension of F that contains both alpha 1 and alpha 2, but we should consider it as the field extension of F of alpha 1, which is generated by alpha 2 here. Okay, right. So now we need to factor in the piece of information that both of these elements are algebraic over the field capital F. Now that gives us an absolutely beautiful understanding of this thing here, the field generated by alpha 1 over F. Okay, we've studied this in the video on field extensions, and we've studied this in the video on algebraic field extensions. We know that if you want to construct that thing, then all you need to do is you need to go through all of the polynomials in the ring of polynomials over the field, and you need to evaluate every last one at this element alpha 1. Okay, you'll get loads of elements that are in the larger field capital L, collect all of those answers together, and that now will be your subfield of L, that is the field extension of F, which will contain alpha 1 here. Okay, it will contain all of F because all of the constant polynomials when evaluated at alpha 1 will be the values in F. Okay, and we know that this subfield will actually be isomorphic to the ring of polynomials over the field capital F, quotiented out by the principal ideal generated by the minimal polynomial of alpha 1 over F. Okay, like so. That's something that we prove in the video on field extensions and then discuss further in the video on algebraic field extensions. Okay, so we have a very good understanding of exactly how to construct this field extension of F generated by alpha 1, okay, if we know that alpha 1 is algebraic over F. So that's excellent, we know how to construct that. Just work out all of the polynomials in the ring of polynomials over the field capital F, okay, evaluate them all at alpha 1 and you'll get loads of elements in this larger field capital L. Keep all of those elements in the set. That's going to be this field here, and it will be isomorphic to this structure here because this is just partitioning the ring of polynomials over the field F into the cosets of polynomials, which will all, when evaluated at alpha 1, be sent onto the same element in L. Okay, so that's why it's isomorphic to this structure here. Okay, if you want further discussion of that, do watch the video on algebraic field extensions where we go into that isomorphism in much more detail. Okay, right. What we now want to consider is extending the field generated by alpha 1 over F further so that it now includes alpha 2. So now producing this field extension of F of alpha 1 generated by alpha 2. Now this isn't so simple. We know that we have a very good understanding if we're trying to build the field extension of F which contains alpha 2, because we know alpha 2 is algebraic over F, so the exact same thing that held true here is true here. All we need to do is look at all the polynomials with coefficients in the field capital F, evaluate them all at alpha 2, we'll get a whole bunch of elements in the field capital L. That subset of capital L is actually going to end up being a subfield that is a field extension of F f, because all of the constant polynomials will be mapped onto f, so they're all in this subset. Again, we know that it'll be a subfield because of the fact that it's isomorphic to this structure, which is a field. Okay, so we have a very good understanding of that, but this isn't that. Okay, this is a field extension of f of alpha 1 generated by alpha 2. Okay, do we know that alpha 2 is algebraic over this field that we are generating the field extension of? Well, not at the moment, but it's very simple to show that it is, and that's the first thing that we're going to show. Okay, so what I want to show now is that if alpha 2 is algebraic over f, alpha 2 is going to be algebraic over this field extension of f. So I want to show that alpha 2 is algebraic over the field extension of f, and this is a very simple argument over the field generated by alpha 1 over f, which is just a field extension of f. Now, to do this, all I need to do is show that the definition of algebraic is satisfied. Now, what is the definition of algebraic? Well, this is the wonderful thing. Even though it looks like a big daunting word, it's a very simple definition. It just means that there has to exist some non-zero polynomial in the ring of polynomials over this field which has alpha 2 as a root. So we need to look at the ring of polynomials over the field f of alpha 1 here, so we now need to be looking at this ring of polynomials here. Now, if alpha 2 is algebraic over f, then that must mean that there was some polynomial in the ring of polynomials over the field f which had alpha 2 as a root. In particular, this one here, the minimal polynomial of alpha 2 over f, that's one of them. All the other ones are obviously multiples of this, okay? Elements of the ring of polynomials over the field f multiplied by this. But that'll do, that's one of them. Okay, so we know that the minimal polynomial for alpha 2 over f, this is some element of the ring of polynomials over the field f which has alpha 2 as a root. Now, this polynomial, its coefficients are all in the field capital F. The field capital F is a subfield of the field extension of f, which is generated by alpha 1. Okay, so this polynomial is going to be in there, because, as I say, all of the elements of f are going to be in there, so all polynomials which have coefficients in f are also going to be in here. So I can instantly conclude that this minimal polynomial for alpha 2 over f is in the ring of polynomials over this field extension of f generated by alpha 1. So that means that there is still going to be a polynomial in here, at least one anyway. There's going to be actually loads of them, but at least one polynomial in here for which alpha 2 is a root, okay, and therefore alpha 2 is going to be algebraic over that field extension of f. Okay, so very, very simple argument. If alpha 2 is algebraic over f, then alpha 2 is certainly algebraic over a field extension of f. Absolutely easy. So, this now means that we can understand how to produce this field extension of f of alpha 1 generated by alpha 2. Again, you just have to look at all of the polynomials from this ring of polynomials with coefficients in this field extension of f generated by alpha 1, evaluate them all at alpha 2, you'll get elements in the larger field capital L, collect them all together, and that then will be your subfield. Now, what's it going to be isomorphic to? Well, you might be tempted to say that it will be isomorphic to the ring of polynomials over the field extension of f generated by alpha 1 here, okay, like so, quotiented out by this minimal polynomial, but that would be the incorrect thing to quotient out by. Okay, this was the minimal polynomial for alpha 2 over the field capital F. This was the unique monic irreducible polynomial which had alpha 2 as a root in the ring of polynomials over the field F. It will still have alpha 2 as a root over here, but you don't know anymore that it's not irreducible. You don't know that it doesn't split now in this larger ring of polynomials into two things that are non-units. Okay? So it may well be the case that there is a new minimal polynomial over here for alpha 2. So there might be a new minimal polynomial for alpha 2 in the field extension of f generated by alpha 1. Okay, and this one will have to have degree less than or equal to this one. It might be the case that this is actually the same as this. Okay, this might still remain irreducible over here, and therefore the minimal polynomial for alpha 2 over this field extension of f is exactly the same as the minimal polynomial for alpha 2 over f. But you can't guarantee that. It might be the case that this now is reducible and there's one of even smaller degree, so you have to now find that one of smaller degree, the unique monic irreducible polynomial with alpha 2 as a root in this new field extension of f, so we'll call it that then. Okay, and then what you can say is that this field extension that you'll get, it will now be isomorphic to this quotiented out by the principal ideal generated by this new minimal polynomial, so the minimal polynomial of alpha 2 over the field extension of f generated by alpha 1, like so. Okay, so that's going to be what this is here. But the point is that we still have an understanding about how to construct this. All this says is that effectively what you need to do is look at all of these polynomials, evaluate them all at alpha 2, you'll get answers that are in this field, capital L, collect them all together. Certain things that you'll get are the elements of the field extension of f generated by alpha 1, because all of the constant polynomials in here will be mapped onto those when you evaluate them at alpha 2. Okay, so this will end up being a field extension of f of alpha 1. But you'll also get some other elements, including, for instance, alpha 2. Just collect all of the polynomials together and collect them all into a subset, and that subset is going to be a subfield of L, because of course it's going to be isomorphic to this, which is a field. Okay, and the reason it's isomorphic to this, just to state it again, is because all of the polynomials that are in a coset of this principal ideal generated by the minimal polynomial of alpha 2 over the field extension of f generated by alpha 1, they are all going to be mapped onto the same thing in L when you apply the evaluation homomorphism pertaining to alpha 2. Okay? All of the things, for instance, in this principal ideal are going to go onto 0, and all of the things in the additive cosets of this are going to be going on to the same thing. That's why there is this deep isomorphism in between those two. And as I say, if you're not familiar with that, do watch my video on field extensions and algebraic field extensions where we explain that. Okay, so this is all working very well. I know how to firstly go from f to f of alpha 1, and then go from f of alpha 1 to f of alpha 1 of alpha 2 in this way. Okay, so I can therefore construct you now the field extension of f generated by alpha 1 and alpha 2. Now let's have a look in more detail what the elements in here are actually going to look like. So the elements in here are going to be polynomials of alpha 2. Okay, that's what I've described doing here. I've described taking all of these polynomials of alpha 2 where the coefficients are from the field f of alpha 1 here, okay, and working out what they are in the larger field capital L, collecting all of those answers together. Obviously you don't put in an answer more than once. If you get two polynomials giving you the same answer when they're evaluated at alpha 2, you only put that answer in once, okay, and that's going to be your field extension. So that means that anything in here is going to be of the form a polynomial of alpha 2. Okay, so how shall I write this? I'll put this here. What should I use for the coefficients? I'll use a. So we'll have a0 plus a1, and I'll just make sure this is in view. Yes, it is. Alpha 2 plus a2 alpha 2 squared plus, and then we might go all the way up to something, and we'll have an alpha 2 to the power of n here. Okay, and of course we'd assume that this n here is of degree less than the minimal polynomial of alpha 2 over the field extension of f generated by alpha 1, because otherwise it would be, the element that you get would be equivalent, the same element as you'd get by a polynomial of degree less than the minimal polynomial. Okay, that's something that we show in the video on field extensions. Okay, that all polynomials are in the same coset in this quotient ring here as a polynomial of degree less than the degree of the polynomial that you've quotiented out by. Okay, right, so we've got some polynomial here, and the important thing to look at now is the fact that a0, a1, a2, all the way up to an, these are all now going to be elements of the field extension of f. Okay, so the AIs are all going to be elements of the field extension of f generated by alpha 1. But now let's remember what those elements actually look like. Those elements are going to be polynomials in alpha 1, where the coefficients are in the field capital F. Remember how we constructed this one up here? Okay, we looked at all the polynomials in the ring of polynomials over the field F and evaluated them all at alpha 1. Okay, so now what I can do is, if you like, replace each one of these with a polynomial in alpha 1 this time. Okay, so I'll just do this for a few of them. So a0 then might end up as b0, 0 plus b0, 1, now alpha 1 plus, let's say, b0, and let's say it just goes up to 2. Okay, so it's only degree 2 polynomial in alpha 1. Okay, so that would now be all of a0 written out now. Okay, so I'll just highlight this in green here. Okay, and then if we do it for a1, a1 now is going to be a polynomial in alpha 1. So it might be b1, 0 plus b1, 1, alpha 1, and let's say it's only degree 1 because I don't want to have to write too much out. Okay, and then we'll have that in front of alpha 2. So here is another one of these. So this is now alpha 1 here. Okay, or rather a1, written out as a polynomial in alpha 1 where the coefficients are now from the field capital F. And then we might go all the way up to an here, and let's say an looks like this: bn 0 plus bn 1 alpha 1 plus bn 2 alpha 1 squared, and let's go up to degree 3, bn 3 alpha 1 to the 3, and now I haven't got enough room, that was a bad idea, never mind, and it will all be in front of alpha 2 to the power of n. So what I'm trying to communicate to you here is that all of these coefficients themselves are polynomials in alpha 1. Okay, so here is one of the coefficients in front of alpha 2 to the n, which is a polynomial in alpha 1. And of course I could multiply all of this out, and hopefully what you understand I would get here is a polynomial in two things, basically, alpha 1 and alpha 2. Okay, so hopefully it is dawning on you what I should do in order to construct the field extension of f generated by alpha 1 and alpha 2 when alpha 1 and alpha 2 are algebraic over f. So I now will state this, okay, and this is the big thing that we've been working up to. So to build this thing, what you should look at is the ring of polynomials over the field in two variables. Okay, so look at the ring of polynomials over the field f in two indeterminates x and y, and now evaluate these polynomials, all of these polynomials, where x is equal to alpha 1 and y is equal to alpha 2. Okay, you will get absolutely loads of answers when you perform this great big evaluation. Okay, and all of the answers will be in the field capital L. So you'll get loads and loads of answers in the field capital L when you do this. Okay, and collect all of those answers together, and those answers that you get, all of the answers, you go through every single polynomial and evaluate them with x equal to alpha 1, y equal to alpha 2, so you consider every possible polynomial in two variables with coefficients in the field f. You ask what will it actually give you when you evaluate it at alpha 1 and alpha 2 in the field capital L. You collect all of the answers together, okay, you will get that this completely contains f because all the constant polynomials will end up all the constant polynomials will be in here, and they, when you evaluate them at alpha 1 and alpha 2, will remain as they are, so you'll get all of f, and you will actually end up getting the field generated by alpha 1 and alpha 2 over f, and I hope that's apparent from this by the fact that all the elements are polynomials of degree, well, in two variables here, alpha 1 and alpha 2, they're in alpha 1 and alpha 2. Okay, so all you need to do then to actually construct this field extension of f generated by these two elements, alpha 1 and alpha 2, is go through all of the polynomials in two variables with coefficients in the field capital F, evaluate them at alpha 1 and alpha 2, collect all of the answers together. That will be a subset of your field capital L, which will contain the field capital F, and I claim that that is your actual field generated by alpha 1 and alpha 2. Okay, so there is the explicit answer of how to construct one of these finitely generated field extensions, and it will only work if the elements are algebraic over the initial field, capital F. If they're not, if one of them's transcendental, then this doesn't work, okay, because you can't guarantee that at some degree it'll turn back on itself. You can't guarantee that it won't go on and on forever, getting higher and higher powers and never fold back on itself unless it's algebraic. You have to have the existence of the minimal polynomials in order to conclude that. Okay, so the elements do need to be algebraic over the initial field F. So that's this in the context of just two elements that you're using as the generators. In the next video, what we'll do is generalize this to having an arbitrary finite number of generators, but I'll firstly have a break whilst you have time to absorb this.